I'm Lech Muszynski, Wood Science and Engineering. I took the liberty of putting my collaborators in here. Samson over there is the PhD student on this project. John Nairin is our resource for modeling. And Fateme Rezai, with whom we've developed some of the methodology for this project. So the project itself is understanding the effect of lamination thickness variation in bond and bond integrity on panel properties of CLT. So thickness tolerance is regulated in PRG 320, right? So there shouldn't be any problem with this. 0.2 of a millimeter, this is the allowed thickness tolerance. We know how to test for bond integrity in cross-laminated timber. You just source from 3 positions in the panel. This is a small qualification panel, not the large one, but there's plenty of area to source these specimens from. You do block shear test, the lamination, and you confirm the bond integrity. These two should assure us that the panels are good. This is one of the test panels. It's moderate size, 3 meters by 2 and something. These are the type of panels that we can do it at the Emerson lab. And if we want to confirm that this has proper bond integrity, we just sample one specimen for the lamination or block shear from each of these areas. And there's like liberty, right? You can take it from anywhere in this area. You test and you're good. Now, I've been always tempted to dissect the entire panel rather than just 3 places and see how it fares, right? And actually, this is the level of the lamination that is allowed. And you see plenty of places where there's more than of the lamination that is allowed. Nevertheless, if you sample from here, you have a good chance of finding a sample that is good. And if it is not, you are allowed to resample. So that way you are playing the game until the panel is confirmed. And this was confirmed, right? So now the question is, what is in the panels that we are putting in structures, right? The thing is that if you look at the way the laminations are oriented, this is not a random thing. It is not necessarily a problem of adhesive itself. If you look at this, it resembles this. So let me just first explain color coding in here. If you like the slightest unevenness of thickness within the lamina, here color coding would be darker, would be like thicker, lighter would be slimmer. You have a trouble putting a pressure on this layer, and it's the same whether the specimen, whether the lamination is a little too thick or a little too thin. Okay, so now things are getting immediately more complicated when you start when you start laminating cross-laminated panel. So they actually start, the troubled areas start to propagate along the pieces that are too thick or too thin. And this is exactly, you may remember, the kind of patterns that we observe here in the actual panel. This one was just simulated, okay? We have the simulation tool here. So our research goal is to try to find out first, how does the thickness tolerance actually affect the bonding conditions? Because in order to bond something effectively, you have to have proper amount of adhesive and proper amount of pressure. If there's no enough pressure, there is not going to be a good bond in there. So whether there is anything to look into this. And then if you have certain amount of delaminations, as we observed in this panel that was actually approved, does it matter for its actual performance? Okay. In order to test that, we devised a couple levels of experimental experiments that I'm going to explain just one in here. Here is a small model of a cross-laminated panel that we've devised. Just, here, 3 layers, 3 blocks in here, arranged that way. If you press on them, if everything is exact the same thickness in the middle, there is no problem. All the load is going to be transferred. If there is a gap in here, however, you will have a lack of pressure in here. And even if this thing deforms and finally makes contact in here, the level of pressure is going to be different than the one designed for the adhesive. Okay. Now, these are built in practice. At first, we played just with dry layups without an adhesive. The question is, how do you measure whether actually there is some pressure transfer from one layer to another? For this, we have optical measurement system based on the DIC principle, with which we can measure the strains on the face of the mock layups. Okay, so this gives us a image that maps strains across this, and then we see if there is transfer. If there is deformation in the central block, it means the load has been actually transferred. If there is not, there is no load transfer. And then we do it in gradation, how much of the pressure is being transferred actually. Before we can do this intelligently, we are talking about strains. Only those can be measured. Stresses cannot be measured. You can calculate stresses if you know the elastic moduli. So again, using the same setup, we measured elastic moduli of all of these blocks that are being used for these mockups. These are elastic moduli representing the two blocks that are on the side. These are exactly the same thickness all the time. We are playing only with the thickness of the block inside in here. And this is the type of results that we get, right? This is deformation. This is actually movement of the crosshead. And here we see strain in the side blocks, blue and green, and in the central block, that is the orange one. And depending on what kind of gap you put in here, you see that the greater the gap, no pressure is being transferred or no strains is being observed actually in the central layer. This is the same thing, but recalculated now, knowing the elastic moduli of individual blocks expressed in stress, actually. So it's somewhat different image, but the same story, right? As the gap increases, you see diminishing load transfer in the central layer here. So here is like very small gap, and then increasing larger gap. The same can be done on 5 plies and 7 if you wish to. It's like once you have it here, it is enough information to start good modeling. Okay. And this is a comparison now of the stresses, level of stress that is calculated using statics with purely elastic assumptions. You see that actually good contact or the contact of lack of contact is actually here with a small gap. And then as the gap between the central piece and the cross layer increases, evidence contact. Well, this is not a very good tolerance in here. Then we are measuring this optical system. We measure within of the total. A preliminary conclusion is that this method is good for our purpose, and it can inform in this areas of this course and so on. Now, level to do the same measurements in the presence of adhesive. Now you have like this there, this thing to be distributed. How much is going to be redistributed if we use this if we don't wait for the adhesive to cure, but just disassemble this thing and just scrap the still wet adhesive and find out if this has been squeezed to the adjacent areas. But also if we allow it to cure, we can then dissect it into delamination specimens and test for delamination and see if what we know about it, I mean, the gap, the lack of pressure transfer, whether it actually translates into delamination, into poor adhesive bond. The next step would be modeling. We would like to fabricate large panels, dissect the entire large panel, now knowing exactly what is the thickness about each of these laminations along the entire piece, and then compare the measurements of the laminations in this each of these blocks with what the modeling would tell us. This would give us a confidence that we can make statements about what happens in panels being manufactured. We explored collaborative synergies with another project that is going to be explained by Vahid, so I'm not stealing his thunder. The plan is also to fabricate and test larger panel in bending and then dissect it to trace what is the failure mode. If the failure mode in the mechanical testing is actually indicative on the poor bonding being the trigger for the failure. That would be all from me. Thank you very much.